Okay, today we are going to discuss a rearrangement reactions, that is a Lawson Lawson rearrangement reaction. So this rearrangement actually involves the conversion of hydroxamic acid or O-acyl derivative of hydroxamic acid into isocyanates just by heating or by using a base. So by taking an example, so this is the structure of hydroxamic acid. Now we are using a base, any base, sodium hydroxide or sodium hydride, any base, and this converts into isocyanates. Now once you get isocyanates, this can be undergoes hydrolysis reaction to give RNH2, a primary amine. The next example, RCO NHOCOR dash. So this is actually O-acyl derivative of hydroxamic acid will undergo a Lawson rearrangement to isocyanates. Instead of using water, if you use any alcohol, so you will get, instead of primary amine, you will get RCO OCO CH3. So this is actually urethane. So the reaction mechanism, the rearrangement, how this rearrangement happens, the mechanism of this reaction, RCO NOH. So we are using a base, sodium hydroxide. So this will take up the H from the nitrogen, and the electrons will be added to nitrogen in order to create a negative charge. I will get Rn minus OH. Now this negative charge make a pi bond. So once it make a pi bond, this R group migrates to electron deficient nitrogen, and once it migrates to the nitrogen, the OH will actually eliminates. So in the next step, we'll get R connected to N with a double bond C double bond O. Now this is called isocyanates. Now this isocyanates undergoes hydrolysis reaction. So the water molecule will act as a nucleophile. It will add to the carbon group, carbonyl carbon, and the electron will be migrated to oxygen because of the more electronegativity. So we'll get OH, H plus, O minus. Now the negative charge again make a pi bond, and this pi electron shifted to nitrogens create a negative charge. That negative charge obstruct a proton and neutralize the positive charge. So we'll get R NH C double bond O OH. Now we have a base. That base will obstruct the proton of the carboxylic group. Now this actually it get a negative charge. That negative charge makes a pi bond, and this bond will breaks, and the electron shifted to nitrogens will get RNH minus plus carbon dioxide, and we have enough water molecule. The RNH minus will take the H plus from the water to get RNH2. Take Examples: methyl CO NH, a phenyl oxygen with a phenyl ring. Now we are using a base. Now it will be converted into the methyl. So the methyl group actually migrates nitrogen. We'll get methyl isocyanates, and this will undergo hydrolysis. So this is methyl isocyanates, methylamine. Here it has to be OCO. There should be CO. So O acyl derivative, OCO. So another example: sodium hydroxide, hydrolysis reaction. So directly we will get NH2, a primary amide. So this is a Lossen rearrangement. So another rearrangement reaction is actually Beckmann rearrangement. So this is a very important rearrangement. So in this rearrangement, when an oxime is treated with maybe mostly ketoxime is treated with a Lewis acid catalyst, such as PCl5, aluminum chloride, POCl3, thionyl chloride, and sulfuric acid. The oxime undergoes a rearrangement to substituted amide. Now we have oxime was treated with Lewis acid catalyst PCl5. Now it will be converted into substituted amide, and these reactions we call it as Beckmann rearrangement, and this oxime is derived from ketone. This is derived from ketone. You can take an example: RCO R dash. First the ketone we need to convert into oxime by using hydroxylamine, and this will give you RCNOH R dash. Now after that we need to use any Lewis acid catalyst, sulfuric acid. Now here one thing we need to remember in the Beckmann rearrangement, that is the stereochemistry, and with respect to the OH group, this R is an anti-positions. Always during the rearrangement, and with respect to anti to OH group will actually migrates. Anti to OH will always migrates. So this group migrates to give R NHCO R dash. So this is a substituted amide. So this reactions we call it as Beckmann rearrangement. Now we will see the reaction mechanism. Of this reaction. So we can take an example of pH acetophenone CH3. We are treating with hydroxylamine. Now we have oxygen lone pair of electron and nitrogen lone pair of electron. The electronegativity is more in case of oxygen, that is why it doesn't donate the electron as much as nitrogen because of the lesser electronegativity. That is why the nitrogen will attack on the carbonyl group. Once it attacks the carbonyl group X, and the electrons will be polarized onto the oxygen. So we'll get pH O minus CH3, get NH2 plus OH. Now this minus will abstract a proton from the NH2 plus. To balance, neutralize the positive charge, we'll get pH OH CH3 NH OH. Now we have the OH group and H group, so it will undergo dehydration, that is the eliminations of water molecule. So we'll get pH, we can write like this, NOH CH3. So this is an oxime, so it's derived from ketones, we call it as ketoxime. Now this will react with acid, sulfuric acid. Now the lone pair of electrons is a poor leaving group OH. In order to make it a good leaving group, this OH will be converted into OH2 plus. This will abstract a proton from the acid. So once it abstracts a proton from the acid, we will get CH3 double bond N OH2 plus. Now with respect to the OH, the pH is the antiposition, so this group migrates. So this group migrates to nitrogen and eliminates a water molecule. So we will get pH connected to N. Now double bond CH3. So the pH migrates with its bonded electron. So therefore the carbon that is connected to CH3 gets an electron deficient, that is positive charge. Now the water molecule, the eliminated water molecule will act as a nucleophile, attacks on the positive charge. We will get pH N double bond C CH3 OH2 plus. Now the lone pair of electrons on the nitrogen will take up H and neutralize the positive charge. So we'll get pH NH double bond CH3 OH. Now it gets a positive charge. In order to neutralize this positive charge, the lone pair of electron migrates here and this comes here. So we will get pH NH C CH3 double bond OH plus. Now we are using a sulfuric acid, so we get HSO4 minus, a base that will take up this H, neutralize the positive charge. So we will get pH NH C double bond O CH3. So this is a substituted amide. So we can work a lot of example for this. The first is the treatment with hydroxylamine. Next is treatment with sulfuric acid or PCl5 or any Lewis acid catalyst. So we will get a oxime. So this is a C double bond N. The stereochemistry of the oxime can be determined by EZ configuration and also identified and confirmed by stereochemical spectroscopic evidences. Now this will treated with PCl5. So this is anti-2OH, this group migrates to nitrogen. So we'll get sulfur connected with NH CO CH3. Wittig rearrangement. So this rearrangement involves benzyl or allyl ethers allyl ethers undergoes a rearrangement reaction in the presence of a strong base. In the presence of strong base, this rearrangement is known as wittig rearrangement. So you can take pH CH2 OCH3. So we need to use a strong base. Here strong base such as alkyl lithium. We can use alkyl lithium, phenyl lithium. So in order to abstract the proton from CH2, so it will abstract a proton from the CH2. We will get CH minus OCH3. Now this is a covalent anion. Now this is not stable one. So in order to make a stable one, this will undergoes a rearrangement reactions. CH minus lithium plus. This group migrates without the bonded electron. CH3 plus. So it is called as electrophilic rearrangement reaction. Without the bonded electron, it migrates and it forms CH3. Because in order to make a bond, we have electrons here, and the oxygen gets electron minus, lithium goes. So this is alkoxide. So alkoxide is more stable. So because oxygen is more electronegative than carbon, so creating a negative charge on the carbon is less stable rather than creating a negative charge on the oxygen. That is why alkoxide is more stable. So if you use H plus, you will get an alcohol, CH3OH. Another example for this wittig rearrangement reaction, pH CH2O CH2pH, phenyl lithium or any alkyl lithium you can use as a base. So you will get pH CH. So this will abstract, because both are same, abstract negative charge. A proton, in order to carry a negative charge, will get CH2pH. This will undergo rearrangement reaction, CH2pH O minus lithium plus, acid work up, you will get pH 2pH OH. So by using an acid workup, we will get this. So it creates a hydrogen from the CH2, a proton, negative charge, will get a negative charge. And once it get a negative charge, this group migrates without its bounded electron to here in order to give this intermediate. This intermediate is more stable compared to this. So after acid workup, we will get this product. This is known as wittig rearrangement. Is actually Smiles rearrangement reaction. So this is a peculiar reaction. So it requires some criteria or conditions. So this type of rearrangement will occur of this type of molecule. So this is X connected nearby ZH. Now here this group should be electron rich, and this phenyl ring should be electron poor. So because electron rich has to attack on the electron poor, so therefore the ZH should be electron donating groups. And X should be electron withdrawing group. So in order to occur this type of rearrangement, the conditions of this type of molecules will occur. Now what are these X? X are NO2, COOH, COCH3 and so on, and Y are oxygen, sulfur, sulfur dioxide, COO minus, and so on, and ZH or HZ is equal to CH2R, NH2, NHR, and OH, SH, and so on. So this good nucleophile. This should be good nucleophile. This is electron donating group. Now we will take an example of this Mine's rearrangement. So we have a NO2 here. Now this is oxygen connected with OH. Now the Smile rearrangement will actually occur this type of the molecule in the presence of a base. We need to use the base, sodium hydroxide. So you will get a product NO2 . So instead of using oxygen here, we can use sulfur dioxide, because in order to differentiate the attacking positions as well as the leaving position. So you will get O. There are 2 carbon, 1 2, SO2 minus. So this is the product in the Smile's rearrangement. Now the reaction mechanism of this reaction. Now first you can write this NO double bond O minus, this is plus. We have sulfur dioxide here, OH. Now we are using a base, OH minus. So this will obstruct this proton and create a negative charge. Why? Because in order to make it more nucleophilic, in order to increase the rate of the reaction, N double bond O minus. Now this is sulfur connected with 2 carbons, O minus, and this O minus, because this carbon is more electrophilic, because it's connected with NO2 as well as sulfur dioxide, so it will be more electrophilic. It will attack here. So we can write like this, the bonded. Once it attacks, this bond migrates here and this group migrates here. Okay, the next step you will get, so this 2 bonds is unaffected. You will get now sulfur connected with 2 carbon along with oxygen connected here. Now we have double bond NO minus, O minus plus. Now after that, the negative charge, again make a pi bond. This group, this pi electron comes over here, this comes over here, this comes, and this eliminates here. Create the negative charge sulfur, and this oxygen goes here. So you will get double bond here. Now this is connected with oxygen with 2 carbon, O minus, double bond, so SO2. So we have NO2. So this is the a lot of examples. This is just sulfur, CH2R, the base sodium hydroxide. We will get, so NO2 as it is, instead of sulfur we will get CH2 will be attacking there here. So we will get CH2 along with 2 carbon, and that carbon contains S minus. So this is the product. COCH3. This is oxygen. Now this is SH, sodium hydroxide. You will get COCH3. Yes. connected with 2 carbon O minus. So this is the product. So this is the reactions with the Smines rearrangement. Now another very important reactions in the photochemistry part, that is actually Barton reaction. Barton reaction. So this Barton reactions involves the conversion of organic nitrite into organonitroso alcohol. Organic nitrate means R connected with O or double bond O into R N O, and this group contains OH as well as N double bond O, some OH. So therefore this is called organonitroso alcohol. This is organic nitrate. By treating with light, this is a photochemical reactions, under it's a photochemical conversions we can write. So it is a photochemical conversion of organic nitrite into organonitroso alcohol. This is called Barton reaction. So you can take an example. So this is OH and this is ONO, alpha, beta, gamma, delta. So in order to occur this Barton reaction, there is an important conditions. The conditions is actually with respect to OH, there should be delta hydrogen should be available. Otherwise these reactions won't go. And with respect to OH, the symmetry of OH and delta hydrogen should be same. Then only the reactions will go. Alpha, beta, gamma, delta, some R group. So this is delta. So with respect to OH, we have a delta hydrogen and they are in the same plane. So now we need to convert this into a organic nitrate by using nitrosyl chloride as well as pyridine. Abstract hydrogen from the OH and create a negative charge. So once it is created a negative charge, we'll get O minus R, and this O minus will attack on N double bond O Cl, attacks here, eliminate Cl, so we will get HCl. So here we are converted into nitroso compound, nitrite. Now with respect to nitrite, so we have this delta hydrogen. We are using a photochemical reaction. Now during the course of the photochemical reactions, it will break, this bond will break up, O double bond N, O, 1 2 3 4, 1 2 3 R group, there is a H, so it will undergo a photochemical cleavage. So once it undergoes a photochemical cleavage, you will get NO radical plus O radical R. Now we have this hydrogen here, alpha, beta, gamma, delta hydrogen. This radical will abstract delta hydrogen. So once it abstracts the delta hydrogen, we'll get OH, 1 2 3 4 R group. we'll get a radical. Now the NO radical will combine here, we'll get OH or NO. So this is nitroso alcohol. This is nitroso alcohol. Now this nitroso alcohol, so this is actually a Barton reactions, the conversion of organic nitrate into nitroso alcohol, and the application is actually, so this nitroso alcohol will undergo hydrolysis to give a ketone, a weak acid. So we will get R. This R group is H, we will get an aldehyde. If R is H, we will get aldehyde as a product. So another important reaction, OH first one is NOCl pyridine, H nu photochemical reaction, sulfuric acid. Now what is the first step? Pyridine will abstract this, we will get ONO. So this pyridine will abstract this H and create a negative charge, O minus. Now this O minus will attack on nitrosyl chloride and eliminate Cl minus. So we will get ONO, a nitroso group. Now after getting this product, we need to go for the photo. So after this reaction, after this step, the photochemical reaction, so we will get O radical, NO radical, so breakage. Now this oxygen radical will identify the delta hydrogen. This oxygen and delta hydrogen should be same plane, delta. So this hydrogen, now this will take up this hydrogen and create a radical over there. We will get radical OH. Now NO radical will combine out here. NO OH. Now this NO will undergo a tautomerization. OH. So it undergoes a tautomerization to give NOH. Now this is an oxide. So we can rewrite this. Can rewrite neatly. This is a bonded electron, so this is, now it is NOH. OH. Now this is an oxide. This is oxide. And the third step we need to use. In the third step, we need to use sulfuric acid. So oxide in the presence of sulfuric acid, it will undergo Beckmann rearrangement. Beckmann rearrangement. So this is with respect to OH, this group is anti portions, this is same portion, so therefore the anti group migrates. So you can write this N. So the OH will take up H2, OH2 plus. So this group migrates over here and eliminates OH2 plus. This group migrates in the Beckmann rearrangement. So here the ring expansion is taking place. The 5 member become 6 membered. So we can take, this is 1, 2, 3, this is 4, this is 5, this is 6. Now this is carbon connected 1, this is carbon 2. Now in 3 we have nitrogen. Now in the second place 2, 3, 4, 5, 6. So in the second we have a double bond. Now in the second position this bond migrates with its bonded electron, so therefore this carbon gets a positive charge. Now we have this OH. Now the OH2 plus eliminated will attack on here, so you will get a substitute, a ring amide, a lactam. This is, we call it as a lactam. A cyclic amide is called as a lactam. So this is the final product in the Barton reactions. Another important reactions with respect to stereochemical aspect, this is CH3. Here we have CH3 and here we have OH, we have CH3, NOCl pyridine, second is H nu. Now what will happen is that the OH group is below the plane. The OH and the delta hydrogen should be same plane. Now we need to find delta. This is alpha, beta, gamma, delta, this is delta. So this CH3 group is also delta, this is also delta, but the stereochemistry aspect that OH is below the plane, it will take the hydrogen below the plane, so this group. So we will get the product CH3, CH2, O, CH2NO, just NO, here OH, CH3. Now this will undergo hydrolysis reaction. The weak acid will get aldehyde, CH3, CHO, OH, CH3. So this is the final product in the Barton reactions.